So I will start with a brief introduction on the I/O forwarding concept, and then present the architecture we set up and some of the results of our tests. So I will then explain how we've set up an IO proxy to ensure fair sharing of the file system resources between several applications. And this will finally allow us to identify the strengths and weaknesses of Lustre in IO forwarding architecture. So what is IO forwarding? So in fact, it's a cluster architecture where the IO operations of the compute nodes are forwarded to dedicated IO nodes, which are called IO proxies. And IO nodes execute IO operations on behalf of the compute nodes. So this provides several advantages. And the first one, it limits the impact of the IOs on the compute nodes. It means it avoids application to have their to be disturbed by the CPU noise of IO processing. And it avoids also applications to have their memory page out because of the page cache usage. So second advantage of this architecture, it reduces the number of file system clients. So having too much clients becomes a problem for the file system because the storage server usually allocates memory structure for each client, and also each client regularly checks server connections and also target aliveness. Having too much clients makes also recovery phase very long, as we have already talked this morning with Nathan. A third advantage of this architecture is it allows to implement additional features on the IO nodes. And for example, it allows to implement IO request aggregation or rescheduling, or also having an additional cache layer on these nodes to absorb bursts of IOs or preload input data for the application, for example. So what's behind our experiments? Actually, our goal is to have a short-term solution that support a lot of compute nodes, but still ensure the interface compatibility with existing applications. So it's sort of intermediary architecture waiting for a more revolutionary solution like with the Fast Forward project, where probably POSIX interface will no more really available. So the goal of our experiment was to first select, set up, and tune each software component. And then we wanted to evaluate the performance in this architecture and compare it with the legacy architecture where the compute nodes are clients of the file system. And finally, we want to identify potential Lustre performance issues of this environment. And this project has been carried out in collaboration with CEA. Here is a test bed of our experiment. So it's made of 8 compute nodes that have 16 cores each, so a total of 128 cores. And at the moment, there is only one IO node, and the storage fabric is made of two OSSs, and one MDS. Nodes are interconnected with 2 separated InfiniBand fabrics with the FDR technology. So these slides present the components of the software stack. On the compute nodes, the application accesses the storage through the v9fs file system, which is based on 9P, the Plan 9 file system protocol. So it's a network protocol developed several years ago by Bell Labs for the Plan 9 distributed operating system. And it's currently, v9fs is a file system implementation. It's a client part of the file system implementation of the Plan 9. At the moment, v9fs is mostly used for the virtual machines on Linux to give them access to the host machine file systems. And its main feature are that operations are synchronous and page cache is not used. So significant efforts have been achieved to make v9fs functional, stable, and performant, especially with the ARDMR layer. So that work has been contributed back to the Linux community. On the IO node, the forwarding function is implemented by Ganesha. Ganesha is an open source project that has been presented last year at LAD by Philippe Daniel. And it's a user mode software that includes a 9P server and a Lustre connection module. So the requests coming from the application are interpreted by the 9P server and forwarded to the Lustre client using the Lustre connection module. And it makes use of the open by feed feature of Lustre. And Lustre is the standard version of Lustre, version 2.4. And most of the tests have been also executed on a legacy architecture, where the compute nodes execute the Lustre client stack and access the servers through a Lustre router for comparison. So now it's time to present some of our results. So the first element we wanted to check is CPU and memory consumption of the compute nodes during I/O processing. So this test was large sequential I/Os on a compute node, and we can see on the legacy architecture on the left graph that the I/O processing represents a significant portion of CPU cycles, and this is in red the system activity. On the right, this is when the compute node forwards the I/O request through v9fs. There is almost no CPU consumption, and it leaves all CPU cycles available for the application. So CPU impact of I/Os on the compute node is minimal, as we expected. So similarly, with the memory consumption, this is the same test, and the legacy architecture, we see that I/O processing consumes compute node memory for the page cache in green, and also for the Lustre internal structure with the slab in pink. On the right, with the I/O forwarding architecture, memory impact of the I/O on the compute node is minimal, and this is what we expected also. So during all root tests, we have been doing monitoring and checked the compute node's memory and CPU consumption, and this is a representative of all the tests. Next test was to evaluate the performance of v9fs and Ganesha components of the stack. So we have replaced the storage fabric with a local in-memory file system on the IO Proxy node. And Ganesha forwards the 9P request to POSIX fsal connection module, which accesses TMPFS through a POSIX interface. So here, the test results of the IOR benchmark executed with sequential I/O from 1 to 8 compute nodes. So on the left graph, the IO node is connected with one InfiniBand adapter to the compute nodes, and the performance reaches 4 GB per second, and it's limited by the stack, by the Ganesha implementation and the IO node consumption. On the right graph, so we connected 2 InfiniBand adapters of the IO node to the 8 compute nodes, and we see the performance reaches 8 GB. So in the first step, the InfiniBand was the limiting factor. The performance is not optimal because it's only 2/3 of the network bandwidth with the FDR technology, but it's almost enough for our test. So back to the full IO forwarding architecture. The test here is an IOR benchmark doing large sequential IOs with 5 per process access using 1 to 8 compute nodes. The performance, which is 3.5 gigabytes in write and read, and which is a relatively good result since it's almost the single client performance for that version of Lustre. And that's logical since all the I/O of the compute nodes are forwarded to only one Lustre client stack. So the same test now, but with a single shared file access profile. And that means all the tasks of the compute nodes access the same file on the storage, and but they write and read on separate regions. So here the performance result is very low. It's only 400 megabytes per second. And the write performance is limited by the Lustre single client. Writes of all the compute nodes are concentrated to the IO Proxy node. And actually the writes of the single shared file are serialized by the Lustre client. And this was to ensure consistency of the write for the POSIX. And I said was because last week, I think, this has been the fix, as I mentioned, the fix for LU1669 has been committed and is landed to master. So we already made measurements with the fixed version, and we see then that the write performance reaches 1.1 gigabytes per second, and this is a dashed blue line on the graph. And now the contention, after profiling, we have seen the contention move to inode address space structure. So for the read performance, it's another story. Here, this is the Ganesha software that limits the boundaries, and the performance is limited by Ganesha because it uses only one file descriptor for every requested from all the client's nodes, the compute nodes. And because it accesses only one file, Ganesha is implemented with one file descriptor. And this messes up the Lustre read ahead, and there is no read ahead activated by this IO profile. Actually, Lustre is not able to identify any read ahead pattern. So we reported that problem to the Ganesha community, and we can hope an improvement. So the red dashed line presents the results of a single client read performance with single shared file access. So we can hope to up to 2.4 gigabytes per second when this is fixed. So next results, it concerns metadata operations. So we use the MD test benchmark to execute file creation, file stat, and file removal on 8 compute nodes in parallel. And the graph presents the results for both IO Proxy architecture and legacy architecture. The performance of the file creation and file removal is very low, and this is an issue we already talked yesterday with Suishi Hihara and Andrea Delga, and it comes from a limitation of the Lustre single client. The MDC component, in fact, serializes the metadata operations, and that's because the MDT is able to handle only one modified metadata operation at a time, because it has got only one slot for reply reconstruction. So we are working with the community, and we opened the ticket 5319, and we are working to address this issue in the next months. What's good with the IO Proxy architecture here is the file stat performance, and that's because Ganesha implements metadata cache, so it benefits for this operation. And finally, here a result with a real application, and so we have chosen NEMO. NEMO is an application used for oceanographic research, and it's a simulation application. And it allows us to configure the number of checkpoints, and so to have a variable amount of data written to the file system. So we made from 1 to 10 checkpoints during the whole execution time. So the graph represents execution time, which means the lower is better. And the results are relatively good, since in the worst case of 10 checkpoints, execution time is 50% longer with the IO Proxy architecture than with legacy architecture. So now we're moving to another kind of experimentations, and we wanted to have IO Proxy nodes used for several small jobs, since it would waste IO Proxy node resources to having small jobs executing or using the IO Proxy node separately. So it means IO Proxy instances are dynamically allocated on the IO node when the job is scheduled, and the IO node instantiates several IO Proxy functions. And the question is how we can ensure a fair partitioning of the file system resources available to the different applications. So we chosen to implement the sharing with the C group and allocated the IO Proxy instances inside the C group where CPU and memory are bounded. And so this graph presents an IO test with only one at a time on a compute node where the IO Proxy instances are allocated different amount of IO node resources. So the blue line at the bottom is for an IO Proxy instance with 1 core and 4 GB of memory. The red line, it's an IO Proxy which were allocated inside a C group with 2 cores and 8 GB of memory, etc. And what is surprisingly good is that the performance is almost proportional to the amount of resources that were given to the IO Proxy, and that allows to bound or to limit the file system bandwidth given to an application just by allocating resources to the IO Proxy instance. So this is the same kind of test, but which is a little more complicated, because we executed several IO jobs in parallel, and there is one IO job on each compute node and one IO Proxy instance allocated for each job. And the first column, we have one job, one IO Proxy, which is given the whole IO node resources. And at the most right column, it's 8 IO jobs in parallel with 8 IO Proxy resources, which are given 1/8 of the IO node resources. And what we can see with the results is that the global performance of the applications are almost stable, for the read at least, and for the write it's almost true except for the 8 IOR instances in parallel. So there is a small gap here that is still not explained, but we were going to explore this issue. So it's time for conclusion. And about our experiment, we still have additional works, and we want to pursue our experiments in 3 directions. First, we would like to execute some additional real application in various simulation domains, and with, if possible, more compute nodes. The second axe of continuation will be to continue IO Proxy sharing experiments, but having using different IO Proxy resources. And the third aspect to explore with this IO architecture will be to have several IO nodes and to ensure, if possible, or as required, the concurrency on the coherency of the file system viewed by the compute nodes with several IO proxy nodes. So what can at least be concluded today is that the IO forwarding architecture requires Lustre single client performance to be very efficient. And this is because IO of several compute nodes are all concentrated on only one Lustre client. So there are at least two IO profiles to be improved. The first one is the shared file access. Even if it's already a fix has been launched last week, we need to continue improve the results. And the second IO profile is a file system modified metadata operation. And just as a remark, this improvement will also benefit to the many core platforms like the Xeon which have a huge number of CPUs, and this platform also requires Lustre client stack to be more efficient with parallel IO processing. Thanks for your attention.
Do you have any question?
So the reason that the proxy doesn't suffers from shared file performance is because it doesn't consolidate any of those requests together, right? Because you're doing synchronous I/O from the proxy. Is that right?
Yeah. Yeah. We at the moment we did not implement any additional feature on the I/O nodes, like I/O aggregation or additional feature.
Is that a possibility?
Yes, sure. This will be an added value even.
Thanks.
Thank you.